Hey, what's up, and welcome back to the fifth and final video of this mini-series, What Exactly is a Container? Now, in this video, we're going to focus a lot more on answering exactly that question. We're going to look into the details of what exactly makes up all the magic that is containers. So more specifically, we're first going to look into the roles of container engines and container runtimes. We're then going to build and start our own container using just the container runtime. We're going to start to appreciate exactly what it is that container engines can do for us. And then finally, we're going to take a much deeper dive into Linux kernel features such as namespaces and cgroups. All right, let's get into it. Okay, so last video we pulled our container image down onto the production host from the IBM Cloud Container Registry. Let's now start by running our Hello World web app container image and then dig a little deeper to see what's happening behind the scenes to make what we know as a container. So let's check the image name again. Alright, so immediately we're reminded that Docker is not installed on this machine. So if you've been following along with the series, you already knew that. We do, however, have access to a very similar tool called Podman. Podman is a container engine, just like Docker, and it allows us to run containers on a host, amongst other things, pretty much just like Docker. Podman is a very useful and important tool for troubleshooting issues with containers running in a Kubernetes environment, where Docker, and therefore the Docker CLI, may not be available, which is fairly common now with the rise in popularity of the Creo container engine, which is actually designed for use with Kubernetes. So in terms of capability, Podman is everything Docker is and more. So like I mentioned in an earlier video, you can create an alias for Docker pointing to Podman, and all your Docker commands will continue to execute just fine. Now, this isn't a deep dive on Podman, so I won't go into a whole heap of detail about the differences because there are a few, but I will show you one of the biggest differences in regards to running containers on a host, so you can see why and how a tool like Podman is useful. So I've got two tabs open here. On the top, we have the production machine with Podman installed, and on the bottom, we have just a machine called Docker, and it has the Docker daemon installed. Now let's spin up two containers on each host. We can just use the small busybox image from Docker Hub and tell it to sleep for an hour. Okay, and let's check the running containers now. Okay, so everything looks pretty much the same, right? The only real difference is that the registry address isn't specified on the Docker host, but we already know that that's because Docker defaults to the docker.io registry. Now, if you look closer, you'll notice that it's not actually the same. So let's take a look at the process trees on both hosts. So here you can see that at the top, which is where we're using the Podman tool, each container has spawned from its own conmon, which is short for container monitor process. Down the bottom, where Docker's running, you can see that both containers have spawned from a parent process called containerd. So this is probably the biggest difference between Podman and Docker. Podman is daemonless, whereas Docker isn't. So if I restart the Docker process, and then check the running containers again, you can see that the containers are now exited. So if anything happens to the container's service, all containers are negatively impacted. If I come back to the Podman host, you can see that if I kill the parent container monitor service from any of the running containers, the pod remains running. You can see here that the container process itself continues to run, and we can prove that even just a little more by getting the container ID and executing a shell inside that running container. So you can see I can still access the running pod. Now, if I kill the pod itself, there's the small issue of an orphaned process because the exited pod hasn't been able to report back through the container monitor process, so it looks like the pod's still running. But I guess that's better than a non-running pod. So in short, Podman doesn't need a daemon process to operate like Docker does, so it's a useful way to query and troubleshoot containers that have been started by other OCI compliant runtime engines like Creo. Okay, so let's continue to use Podman and start our Hello World app with the Podman run command. So again, what we're doing here is running the container in detach mode with the -d option. We're mapping port 7000 on the host to port 3000 inside the container where the web server is running. We're setting the background color of the app to yellow using an environment variable called bgcolor. And then finally, the container name is set to hello world. Okay, we can check the browser to confirm that the app is running as expected. And there we have it. So as always, it's that easy to start our containerized app. We've seen that a couple of times now, but you probably still have at least a few questions like, what actually happened behind the scenes to get that to work? How is the container isolated from other containers on the host and also the host itself? Or maybe even what actually does the mapping of the host ports to the container ports? In my opinion, these are all valid questions, and I believe knowing the answers can really help with troubleshooting container-related problems when things don't really take the happy path. So let's start to answer some of these questions. In terms of what happened behind the scenes, it ultimately depends on the tools used to start the container. So we've been using Docker and Podman throughout these videos, so I'll stick to just these two. But the good news is that regardless of how you get there, the flow is always something similar to what you see here. When it comes to starting a container, the goal of the container engine is to pass something called a runtime bundle to a container runtime. So in this case, that container runtime is runC. runC is actually the OCI's reference implementation for container runtimes. And it was originally donated by Docker to the OCI back when it was called libcontainer. Anyway, what I'm pretty much saying here is that each container engine will have its own features and functions, its own ways of doing things, regular container engine things like providing an API for human or container orchestration software to use, or providing functionality to pull and push images, preparing container storage like setting up the copy on write layer and prepping any mounts when you start running a container, and also sorting out the networking for the container as well. But no matter what, preparing this runtime bundle to pass onto the container runtime of choice is something each container engine supports in the same way, because it's the container runtime software that's actually where a lot of the magic happens in terms of making a container into a running environment. Okay, so we know now that the container engine generates a runtime bundle, but what does this runtime bundle look like and how do we actually get a runtime bundle? Well, first we need our image available in OCI format. So we just want to get that Hello World version 1 image into OCI format now. So from the last video, we know that we can get that pretty easily using Scopio, and we can get that from local storage too, rather than having to download it again. Okay, now that we have our OCI formatted image, we can generate a runtime bundle just like the container engine does. So for that, we can use a tool that's recently been incorporated into the OCI called Umoci. So as per the Umoci site, the Umoci unpack command allows us to take an image and extract its root file system and configuration into a runtime bundle, which is what we now know that runC, the container runtime, is expecting. So you can see there's lots of files in our runtime bundle. If we go into the runtime bundle, we can see that there's a config.json, and the config.json contains a lot of the necessary config to start the container. You can see here that we've got the args, we've got environment variables, we have the capabilities of the container on the host, and we also have some namespaces listed that we'll talk more about in a moment. Now you can also see that the root file system has been extracted. And this obviously contains all the files that are made up from the various layers of the container image. Okay, so let's now use the container runtime that's called runC to run the runtime bundle and start the container. And there we have our container running. So you can see that the web server has started inside the container on port 3000. Now, we can't access the app like this because a function of the container engine is to actually do the networking setup for you. And I skipped that part because I think it starts to become more of a virtual networking video rather than a video focused on containers. Also, the specifics change a lot between the different container engines that you may end up using too. So instead, I created this slide that points out at a high level what each container engine does to network the containers that it starts. So first of all, we see that when the engine is installed, it creates a bridge on the host with a new network address for all the containers that will run on that host. Then when a new container comes along, it creates a new virtual interface and it connects that virtual interface to that bridge. The container engine then creates a new network namespace and then it adds the virtual interface to that namespace. So this namespace is then later associated with the new container. So this is effectively like plugging in a NIC that's already connected to the host bridge into the container so that there's connectivity between the container and the host. Finally, the container engine assigns the virtual interface inside the container an IP address on the host container network, and then it configures the default gateway to hit the bridge. And of course, it brings that interface up. So yeah, the container engines are definitely handy, doing all this behind the scenes for every container that you create. And you can actually see some of this with Podman. So let's get a new tab. So if you take a look at the interface config, you can see that there's this Podman network, and CNI, by the way, stands for Container Network Interface. You can also see that there's a virtual Ethernet device that would be assigned to our running container. We can have a look at this by checking the interface config of the running container. And we can see that the interface inside the container is running on the same 10.88 network of the CNI Podman 0 network. If we were to stop that container, we would see that the virtual interface would be removed. Okay, now amongst all of that, I mentioned namespaces a couple of times, and I realize that you may have no idea what that means at the moment, but just park that for one more minute because I've got some good examples coming up that we'll explain. For now, I just want to finish up on the topic of the container runtime, runC. So we now know that runC is most often the tool that will actually run our containers, regardless of the container engine that we're using. So it's also a good tool to check on containers when you're having issues with the container engine itself. Now, we previously stopped one of the containers that we started running with Podman, so let's just start that up again. So we can use runC to perform some checks on our running containers directly. Now we can actually use runC to look at all the containers started by runC by running the runC list command. Here we can see that we've got the container that we started directly with runC, and we're also seeing the container that was started with Podman. We can also have a quick look at the processes running inside a container with runC. You can see we've got our next application running. If we want to, we can also get a shell into a container using runC. And you can also view events directly from the container. Now, by default, that will display events every 5 seconds, but you can get them once off as well with the stats option. Okay, cool. So now we know what a container engine does to start a container. It calls out to a container runtime with a runtime bundle that it prepared after preparing some storage and network resources. The next question would be, how does the container runtime then ensure that the process, that is the container, is running in an isolated environment, its own host name, network, file system, and all that sort of stuff? The answer to that is that it uses a Linux kernel feature called Namespaces. So namespaces, as you would expect by the name, limit the visibility of system resources. So to give an example, if you're in a custom network namespace that only has one NIC assigned to that namespace, you'll only be able to see and therefore interact with that one NIC, even though there may be 10 other NICs that exist outside of the namespace on that host. So first of all, we can read more about the different types of namespaces available by looking at the man page for the nsenter command. You can see here a short description for each of the available namespace types. We can look at the namespaces associated with the process with the list namespace command. First, we need to get the PID of the container process, and then we can list the namespaces. So our container process is a member of these namespaces. We have the cgroup namespace. We'll talk more about cgroups in a minute. The user, network, and mount namespaces. We then have the UTS namespace, which handles things like hostname. The IPC namespace that deals with system message queues. And finally, the PID namespace, which gives the process its own PID tree. So it's these namespaces that make the container feel like it's a separate functioning system. They're created new for each new container, and they mean that each new container can only see the system resources that have been placed in its own namespaces. It's also really a combination of them all, because one here and there really wouldn't give the same effect. For example, at the moment we're in the host's namespaces. We can see them by listing the namespaces for the process ID 1. And we can see that we have different network namespaces. So if I look at the interfaces on the host, we get 4 different interfaces, but if I enter the same network namespace as our container, things will look a little bit different. You can see that I can only now access the network resources available in the container's namespace. So we now only have access to the container network interface and the loopback interface. Now you can also see that we're still in the UTS namespace of the host machine because our prompt is still showing production. Let's move into the UTS namespace of the container as well. And there we go, our host name has now been updated to the container ID. Okay, so we can exit out of those namespaces. So that's just an example for getting into a couple of namespaces, but an easier way to enter into all of the namespaces is with the --all option, or the -a for short. This time though, because we're also entering the mount namespace, we'll need to specify a shell. And there we go, we've entered into all the namespaces of the container and we can see the container's file system again. Okay, so hopefully that gives you a better understanding of the power of namespaces. If you're familiar with the term pods, perhaps from Kubernetes, or Podman 2 for that matter, you can probably see how different container processes can be joined to the same namespace to share the resources of that namespace. Anyway, that's enough on namespaces. The other significant piece to the puzzle is control groups. So control groups, or cgroups for short, can be used to limit the resource usage of a system resource, like CPU, memory, disk, and network. You can see the system cgroups available here. And more specifically, we can see the cgroup settings applied to our container. So what we can do is set resource limits using the container engine. So in this case, obviously Podman, which will then create these cgroup configs for us and impose the limits on the container. Let's start up another container on a new port with a different color background so it's easier to tell the difference. And also limit the amount of memory the container can use to 1 GB and the CPU quota to 0.5 of a CPU. Okay, so we now have another container E7E started. So what have the -m and the --CPUs options actually done, and how can we see it work? Well, in terms of what it's done, we can have a quick look at a few things. First of all, we can look at the memory. We can look at Podman inspect. Okay, here we can see the memory configured for the container, which is in bytes, so that makes up approximately 1 gig. If we have a look at our other container that hasn't had any memory limit specified, we can see that we get a value of 0. Now let's look at the cgroups. I'm going to open up another tab because it makes this a little bit easier. So first, let's just check out the host. So this is the cgroup that the host abides by for the limited amount of memory in bytes. It's just a really big number that effectively means infinite. Let's take a look at the same thing inside the container. And here we can see that inside of the container, the exact same file is showing that we have a 1 gig limit. So back on the host, we can actually see where this container limit is configured. You can see there is this machine slice directory. And this directory houses all the cgroup config for each one of our containers that we spin up with Podman. We can go into our memory limited container. And we can have a look at our memory limit in bytes again. So you can see this is where the 1 gig is specified on the host. Okay, now we can look at the same sort of information for CPU as well. So we can see that our CPU limited container is set to 50,000, which is the 0.5 of a CPU that we specified. If we take a look at the container that doesn't have CPU limited, we can see that there's no limit imposed. Now again, let's take a look at the cgroups. First, we can see the cgroup of the host itself. We can see the host has the configuration of -1, meaning that there's no limit set. Let's take a look at the exact same file in the container. And once again, the view from inside the container shows us that the host believes that it only has access to that 50,000 or 0.5 of a CPU. And lastly, we can just take a quick look at where this configuration is specified in the context of the host. And there we have the same 50,000 limit set. So you can see that if I wanted to increase the amount of CPU quota available to the container, I can update that config. And we can see that it is reflected inside the container. Now I'll just change that back for the next example. And finally, we can check that these limits actually can't be breached. So when we built the container image, we included a tool called stressng that will help with this. So we've already got a shell into the container down the bottom. So let's test the CPU first this time. We'll just check and confirm that this machine is configured with only one CPU. And we can see that there's only one CPU core available. Now let's run a stress test in the container trying to use all of that one CPU, keeping in mind that we've specified that only 0.5 of a CPU is available when we actually created the container. So you can see that the process is limited to pretty much exactly 50% of the CPU. So what happens if I stress test with, say, 2? So again, all the running processes in that container are limited to the 0.5 CPU that we set. So they evenly share the usage. Cool, so let's now take a quick look at memory too. Now, the difference between CPU and memory is that it's a lot easier to keep a CPU in line without getting the container killed off. But if a container was continuously asking for more memory, the container engine will out of memory or OOM kill the container. Anyway, let's give it a go and see what happens. So I've now got the top command running with a focus on memory in the top panel. So here we can see that we have about 3,682 megabytes of RAM available on the host. But we know that our container is configured to only use at most 1 gigabyte of that. Now, before I continue, I should just mention that I've had to increase the CPU allowance from 0.5 of a CPU up to a whole CPU, because I found that when doing the memory stress test, the container wasn't able to get full use of the 1 gig memory with only half a CPU. So let's start the stress test. We can push this a little more by running 2 workers. And that's a better example where we know that the stress test is trying to gain access to 4 gig of memory, but we can see from the resident size, which tells us how much physical memory is being consumed by a process, that it's capped at most 1 gig. Alright, and there we have it. That wraps up this mini-series. Now, I hope that you enjoyed the series, but most importantly, I hope that you learned something new. So if you did, please consider hitting the like button and also the subscribe button so that you can stay up to date with the latest videos that I release. Awesome. Thanks again, and bye for now.